Hey everyone, welcome back to my another tutorial, and as you can see here I have again opened my Jupyter notebook. So this time we'll build our first neural network in TensorFlow. So in this tutorial part we'll do that, and remember that there are two parts of implement of TensorFlow model. So one of them is create the computation graph, and second one is to run the graph. In this part we'll use same cats versus dogs dataset we used in our previous tutorials, but in this tutorial, instead of using sigmoid, we'll use softmax function. So if you want, you could add more classes to recognize. Also, because we'll use softmax, we'll need to change shape of our labels. So I made a convert to one hot function, and if you watch my previous tutorial, you know what it does. So adding to this, our use data shape will be a little bit different than we used before. Well, everything is in these few lines. So here I'll import our necessary libraries for my tutorial. So here in this line I'll use first my GPU. I have few of them, but instead of using CPU right now I'll use GPU, so I wrote so. And here is my parameters. So I will convert all images to 64 by 64 size, and all of them will be 3 channels, so RGB, and we'll use only 2 classes here, so it will be cat and dog. So here is my same prepare dataset functions as I used before. This is simple to read images and resize it to our required size. Then I'll use prepare data, so it's with the labels and so on. And if you will be adding more classes than one, so you'll need to change this a little bit in dataset and so on. So you should do this by your own. And here is my one function convert to one hot. So yeah, I talked about it a little in my previous tutorial. So I'll build this all rows, and here I have my dataset, and right now as you can see it's preparing my data, so it's looping through my folders as I have a lot of images for training. So here in the last lines, as you can see, I'm doing everything a little bit different. I'm calling my one hot vector, so I'm reshaping labels. And here before we used something like this, and right now we are multiplying all my row columns and channels and adding and transpose. So anyway, as it loads in a moment, I'll use my print function and I'll print it out, and you can see our shapes. As usual, here we flatten the image dataset, then we normalize it by dividing it by 255, and if it won't be in an image, we don't need to normalize it. We should use different techniques of this. Let's wait for loading our dataset. So our dataset was loaded. Right now I can print the shapes for you, and as you can see we have 6,000 of training examples, 1,000 of test examples, and here is our shapes as you can see. So note that 12,288 comes from multiplication of rows, columns and channels. Each image is square, 64 by 64 pixels, and 3 is for RGB channel. And please make sure that these shapes make sense to you before continuing on this tutorial. So our goal is to build an algorithm capable of recognizing a cat and dog with high accuracy. To do so, we are going to build a TensorFlow model that is almost the same as one we have previously built in NumPy for cat recognition, but now using a softmax output. It's a great occasion to compare our NumPy implementation to the TensorFlow one. So you will see that training of model on TensorFlow is significant faster than on NumPy. So our model will be linear ReLU, linear softmax model. The sigmoid output layer has been converted to a softmax, and softmax layer generalizes sigmoid to when there are more than 2 classes. So I added this that you could simply play again with more classes. So first we'll be creating our placeholder for x and y. This will allow us later to pass our training data in when we run our session. So here is a function to create a placeholder in TensorFlow, and I won't talk about in arguments and returns, and if you want you can read it later on my webpage or on my GitHub repository. It's up to you. So I'm just building this, and for example right now I'm building this, and as you can see outputs were just simply tensors of x and y. So next we'll implement the parameters layer, initialize parameters. So we are going to use Javier initialization for weights and zero initialization for biases. So it's not that difficult, and here as we are using 2 hidden layers, I wrote that it will use input h1 h2 hidden layers and will use output. So inputs should be accordingly made. So I wrote here a test of, for example, if we use our images, our input would be X training shape of 0 and output will be of classes, and here you choose what you want. Well, for this example I chose 25 to 12, and actually we can print it out and we'll see what we receive. So print nothing. Oh, nothing, it's loading something, so we'll see in a moment. Yeah, it's old stuff here. So yeah, it was printed out here, and as you can see you see shapes which we have our variables initialized, and yeah, we can move forward as quick as possible. Next it will be our forward propagation in TensorFlow. So now we'll implement the forward propagation module. So the function will take in a dictionary of parameters and it will complete the forward pass. So the function we will be using are adding, multiplying matrix, and making a rectified linear unique activation. Now I should say a note that I commented a NumPy equation so that you can compare the TensorFlow implementation to NumPy. So it is important to note that the forward propagation stops at Z3. So the reason is that in TensorFlow, the last linear layer output is given as input, the function computing the loss. So therefore, you don't need to have A3 here. So let's build this. Build. And here I have an example here, and we'll call it. So we're creating a placeholder as we created before. We are initializing parameters, and right now we will do a forward propagation. So let's build this. Z tensor as shape of shape 2 and unknown. That's cool. It works. So you may have noticed that forward propagation doesn't output any cache, and you'll understand why when we get back to our back propagation place. So right now we will go to compute cost. So as seen before, it's very easy to compute the cost using following function, as you see here, cross softmax or center period left logits and so on. But it's important to know that logits and labels inputs of this function are expected to be shape of number of examples and number of classes. So I have transposed Z3 and Y for you, so you don't need to mess with your code. Besides, the TensorFlow reduce mean basically does the summation over the examples. So here is our cost function. It's quite simple, very simple. Compared with NumPy, we are just reading our logits, labels, and so on. And okay, I'll build this, and here we are doing actually same stuff as we were doing before, But now, after forward propagation, we compute the cost. So I'll build this. Okay, I'll build this again. And as you can see, we received our cost and it's saved in a tensor. Okay, and now we can move to our mini batch gradient descent because we'll use it in our training loop. So we'll build this from the training set X and Y in 2 steps. So first of it will be shuffle step. So we'll create a shuffled version of the training set X and Y as shown in this image. I can zoom in. As shown in this image, and each column of X and Y represents a training example. And note that the random shuffling is done synchronously between X and Y, such that after the shuffling, the ith column of X is the same example corresponding to ith label in Y. So the shuffling step ensures that examples will be split randomly into different mini batches. Well, it's faster for training purposes. Well, actually, and it works in practice. So next step is partition. So we'll partition the shuffled X and Y into mini batches of size mini batch size. And note that the number of training examples is not always divisible by mini batch size. The last mini batch might be smaller, but you don't need to worry about this. When the final mini batch is smaller than the full mini batch size, it will look like this. And you don't need to worry, of course, as I told. So we'll calculate the last mini batch, and here will be, for example, 40 examples, 30 examples, it doesn't matter until it exceeds 64. So okay, and we don't need to waste a lot of time here. Also, we can move up to our function. So here we have our mini batch size for in this example as default is 64, and I won't explain this code because, well, actually you don't need to understand it. So we'll just build this and I'll run the mini batches of my dataset. And as you can see, as I have for example, mini batch of 64, we receive 94 mini batches. So that's quite nice, and we'll do all the training with all of them. So what we should remember from this, that shuffling and partitioning are the 2 steps required to build mini batches, and powers of 2 are often chosen to be the mini batch size example. 16, 30, 64, 128, and so on, doesn't matter. And well, I recommend to choose the size you need. But right now we came to the most exciting part. So backward propagation and parameters update. So this is where we become grateful for programming framework. All the propagation and parameters update is taken care of in one line of code. It is very easy to incorporate this line in the model. So after we compute the cost function, we'll create the optimizer object. This like optimizer. So sorry, I shouldn't do this. Optimizer object. We have to call this object along with the cost when running the TensorFlow session. When called, it will perform an optimization on the given cost with the chosen method and learning rate. For instance, for gradient descent, the optimizer will look like this. Gradient descent optimizer, learning rate we choose, and what we want to do, we would like to minimize the cost. To make the optimization, we would do something like this line. So this computes the backpropagation by passing through the TensorFlow graph in the reverse order from cost to input. So we only use C, we won't use this small slash, bottom slash, I don't know how it's called, doesn't matter. So we'll build the model. Finally, we made for all the steps required. Now we'll bring it all together. We'll be calling the function we had previously implemented. So we'll implement a 3-layer TensorFlow neural network. So it will be linear ReLU, linear ReLU, linear softmax. If you're interested, you can add more, but for my example, I'm using 2 hidden layers. So there is arguments and returns. It doesn't matter for us right now. Well, if you're interested, you can get deeper into it, but as I'm not using them for now. So actually, here is all my model. And what we do is that we prepare our data set. So we have a cost list where we place our cost. We create placeholder. We initialize our parameters. I will use 200 neurons in my first hidden layer and 20 in second layer. I don't know what result will be, but let's try this. And next, for propagation, we'll build the. That's quite simple. We call X and parameters, then we compute the cost, and then we use an optimizer. I'll use Adam optimizer. If you didn't hear about them, I recommend to read about this on the internet, but actually we mostly always use Adam optimizer because it's the best. So we initialize all the variables here and start the session to compute the TensorFlow graph here. So at here we are running the session, and here we are working with mini batches. And also I won't talk about this much, but as you can see here, we are running the session and we are running another session here where we try to optimize our cost function, and we feed our mini batch of X and mini batch of Y. So yeah, and yeah, that's it. And here I use a print function to print my cost every 5 epochs, and I'm saving them to the diction list here, which we'll plot later. So for now, this will be the plot. Here I'll save the trained parameters to my parameters dictionary, and here I calculate the predictions, and here I calculate our accuracy on the test set. And actually here we are printing our saved results, and here I am saving my model. So if you don't have a GPU or you don't want to waste your time, you'll be able to download my model, load it, and test how it works for you. So for now, let's run the following line and our training will begin. It will take for me about 15 minutes on my GPU. So I'll just stop my recordings and train it, and later I'll return when it will finish. Okay, so I'm just starting my, oh sorry, I didn't build my models. So here I'm starting to train my model. As you can see, here is kernel Buzzy, so it says that we are training my model. So okay, I'll return after my model will finish training. So welcome back again, and I see we already finished training, and it is 1000 of training steps. And let's see what results we have here. Oh, they're not that great, but as you can see, training accuracy is 1.0. That's actually impossible, but actually that's amazing that our algorithm can recognize a cat and dog with 59% accuracy. Well, okay. For now it's okay. Maybe if I change some parameters of my network, it might be different, but well, anyway, we have what we have. I won't do it again. So our model seems big enough to fit the training set well. However, given the difference between train and test accuracy, we could try add something like L2 or dropout regularization to reduce overfitting. because you might see this very big difference in accuracy. And think about the session as a block of code to train the model. Each time we run the session on a mid-batch, it trains the parameters. So in total, we have run the session a large number of times for amount 1000 epochs until we optimized well-trained parameters. And as you can see, there's few crazy spikes, and maybe there is something with dataset or so on, I don't know. But yeah, there is something bad. So this means that our model doesn't work very well for image recognition. So in next tutorial we'll try something different. You'll see this will be amazing. I won't tell you right now. So anyway, let's move forward. Now we can take a picture of our cat or dog and see the output of our model. To do this, here I wrote this function here, and okay, let's simply build this. So here is another predict function, and here we create a placeholder, and we use for propagation, and again we use softmax to predict our model. So here it is, and let's build this, and let's try to see what we receive. Yep, it gave me 1 with a dog. That's right, that's correct. And if I'll give a cat, let's see what I'll receive. And it should be 0. Yeah, it works. That's perfect. Our model works with saved parameters. So next I would like to talk about restore the graph from meta file, because here we saved our model to this meta graph, and right now we would like to see how we can use it without training our model again. So when we save the variable, it creates .meta file. This file contains the graph structure. Therefore we can import the meta graph using following line, this line, and restore the values of the graph. So let's import the graph and print all the tensors in the graph. So this way we should print it out. And yeah, okay, yeah, I just print it out. And as you can see, here I printed everything I needed, everything our model has saved to a file. And going forward, now that we have the imported graph, we know that we are interested in W1, W2, W3, and so on tensors. So we can restore them from parameters in following code here. And if you want, you can uncomment these lines to print them out. I don't want to print because I'm sure it's the same. So we simply create the saver here from our file, and here with this line we restore what we have there, and simply we just run the session and with following names in our tensors. So I'll build this. Okay, it writes that in a new version we do something different, it doesn't matter. And here I have so I saved a new parameters, and with this line I will test again our parameters with X image we had here. So I just need to call this, run, let's build this. Oh, it worked. 0. And if I'll change this again to dog, okay, I'll just save it, and here I will run it again. It will predict me a dog as 1. So that's wonderful, it works. So I should congratulate you with finishing your first deep network with TensorFlow framework. And what we should remember from this tutorial: so at first, TensorFlow is programming framework used in the deep learning. Second, the two main object classes in TensorFlow are tensors and operations. Third, when we code in TensorFlow, we have to take the following steps as create the graph containing tensor and operations, create session, initialize the session, and run the session to execute the graph. Then we can execute the graph multiple times as you have seen in my model. And the backpropagation and optimization is actually done when running the session on the optimizer object. So you can play out with your image dataset or not image, it's your choice. Just simply prepare your data for neural network model. So in next tutorial part, instead of using simple deep networks, we will use convolutional networks. We will see what difference we'll get on the same dataset. So thank you all for watching. I hope this tutorial was useful for you. And of course, subscribe my channel, like this video, share it, and see you in our next tutorial.